Okay, so our last part about inequalities with triangles is called the triangle inequality theorem, an extremely important theorem. In fact, it's kind of odd that we save this for the end um, of a unit. The triangle inequality theorem tells us whether we even have a triangle or not. We learn all these rules and properties about triangles, but this is the one that determines, can we even make a triangle from the segments that we have? Um, so all triangles have three sides, but can any length segments form a triangle? Keeping in mind that to form a triangle, the segments can only meet at their endpoints. And we can go through some experimentation. For example, if we had measurements, segments that measure 6, 10, and 20 units, whether that's inches, feet, doesn't matter, you can see that if I connect the 10 to the 20 and then the 6, it doesn't even reach. Like 10 plus 6, it doesn't even reach the other end of the 20. And that's really the heart of this theorem. There's a few slides that kind of document a few examples here, but the 10 and the 16, it wouldn't even reach the other end of the 20. If I had a 14 and a 16, it does reach the other end of the 20, but 14 plus 14, I'm sorry, 14 plus 6, not 16. 14 plus 6 is 20. So it will reach the other end, but it's just going to lay flat. They're exactly 20. The problem is that it's still not a triangle. It's just two small segments laying on top of a bigger segment. And even though it reaches the other end in this case, it doesn't form a triangle. But if we used 16, 6, and 20, that would form a triangle. Okay. So think about it in the sense that when it was 16 plus 4, it reached the other end, but that's it, it laid flat. When it's 16 plus 6, it would, if we laid it flat, it would actually stick out past the 20. But if we pinch those two pieces together, so if I take these two pieces, these two ends, and I'm going to pinch them together, then it's going to cause that center vertex to pop up where they stick together. And now I have a triangle. So to summarize it, we can say if having issues here, if the sum of the two smaller sides is greater than the longest side, then those measurements will form a triangle. So the sum of the two smaller has to be greater than the third side. And if that's true, that forms a triangle. So let's test a few questions if they can form a triangle. So we're going to test it. 7 plus 10 greater than 13. Well, that 17 is greater than 13. That's true. That's yes. So this does form a triangle. 12 plus 16 is that greater than 34. Well, 12 plus 16 is 28. Is that greater than 34? No. So that does not form a triangle. Remember, we're asked to determine if the measurements can form a triangle. The sum of the two smaller sides has to be greater than the longest. 9 plus 11, is that greater than 20? Well, is 20 greater than 20? No. The sum of the two smaller is what we're testing. 23 greater than 24? Again, that's a no. (17 plus 26), is that greater than 42? Well, 17 plus 26 is 43. So that's a yes. It does form a triangle. And 7 plus 7 greater than 10. 14 is greater than 10. So yes. Again, the sum of the two smaller sides must be greater than the third side. If that's true, we form a triangle. Now, we can also use the triangle inequality theorem to determine the possible values of that third side. So if I know two segments, if I know two sides of the triangle, I can figure out what are all the possible values for the third side. And the next couple slides go through a few examples. We don't know if that third side is the smallest, the medium, or the largest, so we have to test. And first, we can assume that the missing side is the smallest. So we can say the x plus 10 has to be greater than the 15. And we find out, well, x has to be bigger than 5. But can it be a million? Well, no. There's a limit. We can test when our missing side is in the middle. So we get 10 plus x. And that's what we just tested. So middle doesn't matter. What we really want to concern ourselves is, what if our missing side is the smallest? What if our missing side is the biggest? And that's going to give us our range. So in our last example, we're going to assume that the missing side is the biggest. So now we have 10 plus 15 greater than x. And we find out that x has to be less than 25. So in the first example, we found out that it had to be bigger than 5. And in this one, we found out it had to be less than 25. So here's our summary. In our first example, if it's the smallest, it still has to be bigger than 5. And if it's our biggest, it has to be less than 25. It cannot be 5 or 25. Remember, the sum of the two smaller sides must be greater than the third side, not equal. So we found out our lower limit and our upper limit. Well, as a simple shortcut, we can subtract the two known measurements to get the lower limit, add them to get the upper limit. Just to kind of summarize the examples that we went through. So we want to determine the possible measurements for that third side, given the two sides. So again, what we're going to do is subtract and add. When we subtract, we get 3. When we add, we get 23. So our third side is between 3 and 23. We could say 3, literally write it between them, and then fill in your less than symbols. So 3 is less than the measurement of our side, and our side is less than the measurement, less than 23. We can say this a few different ways. X is greater than 3, and x is less than 25. X cannot be 3 and x cannot be 25. It must be a number between 3 and 23, sorry. It must be a number between 3 and 23. It could be 3.1. It could be 22.99, but it cannot be 3 and it cannot be 23. So let's look at a couple others. Again, we're going to subtract, so 34 minus 12. We're going to add, and our third side between 22 and 46. And again, we can write this a few different ways. Let's look at another one. If we subtract, we get 2, and if we add, it's 20. So between 2 and 20, 2 is less than x, which is less than 20. We can write inequalities. Looking at number 4, let's turn the question a little bit. Can the third side be 10? Well, if we add, we get 32, and if we subtract, we get 16. So can the third side be 10? No. It has to be between 16 and 32. 10 is not between 16 and 32. So we could be asked, what's the possible values or the range of values? We can be asked, can that third side be this value? And our answer is no, in this case. So that was number 4. I'll do number 6 also. I'll just skip 5 just for space. Can the third side be 15? Well, again, when we subtract, we get 3. When we add, we get 17. So it must be between 3 and 17. So yes, it could be 15. We're not saying it is. We're saying it could be. Okay. And finally, again, we're determining if our points here can form a triangle. And we've got a couple different approaches. One, we can graph. It's either a line or a triangle. 2, we can do slope. If all points produce the same slope, then it's a line. So, for example, if this was point A, B, and C, we would do the slope of AB, slope of AC, slope of BC. If they're all the same, then it's a line. And option 3, distance formula, then test the theorem. So we'd use distance of AB, distance of AC, distance of BC. Add two smaller numbers and test if it's greater than the third number. That's exactly, now option 3 is the one that we've done this entire lesson. We added the two smaller numbers to see if it was greater than the third number. But here we would have to do distance formula just to get those numbers. An alternative is to use slope. And if they're going in the same direction, like it's impossible for a triangle to have parallel lines. So if you get two slopes in the same direction, if you get two slopes with that are the same, then that means that they're either parallel or physically the same line. Well, again, in a triangle, all three sides are going in different directions. They all have different slopes. So if you get two slopes that are the same, it can't be a triangle. And a graph is a nice picture, but we have to be able to do it algebraically. So we must be able to do it algebraically. Okay, that is a necessity. So again, this is an exercise that you can complete, and we can use slope or we can use distance formula. So I'm going to label my points A, B, and C, and I'm going to find the slope of AB. That's -4 minus 3, -2 minus 6, -7, -8, so 7/8. I might find the slope of AC, 4 minus 3, 2 minus 6, so that's 1, -4. And now I'm going to test the slope of BC, 4 minus -4, 2 minus -2, that's 8/4, or 2. Since my slopes are all different, this is a triangle. For number 2, again, I'm going to call it point A, B, and C. And I'm just going to give myself some room here. And I can find the distance. Let's do distance of AB. So square root. So for our distance formula, we have something like -1 minus -5 quantity squared, 1 minus -3 quantity squared. -1 under the square root. We have -1 plus 5 is 4 squared, and 4 squared. 16 plus 16 square root 32. And since I don't really want to round if I'm going to test all this, but let's see how these numbers work out. We have distance of AC. Uh, 4 minus -5. 6 minus -3. So that's a 9 squared. 9 squared, all under the square root, 81 plus 81, 162. All right, so we're going to have to do some rounding here, and we're going to trust that it doesn't mess up our numbers too bad. Well, maybe we'll go to the hundreds to have some accuracy. And then finally, I'm going to do distance of BC. So distance formula here. 4 minus -1. 6 minus 1. So I'm just going to give myself a little bit of room here. I'll scroll back. It's 5 squared, 5 squared, 25 and 25, square root of 50, 7.1. And now we would test adding our two smaller numbers, 5.66 plus 7. Let's do hundredths to be consistent. And we're testing, is that more than 12.73? And it clearly is. It's actually exactly 12.73. 12.73 greater than 12.73, and this is no. So this is not a triangle. All right, so as long as we're consistent, whether we're going to round to the tenths, hundredths, as long as we're consistent, we should get good results. But it does require some rounding, and that has potential to change things up a little bit. So again, graphing it is nice. It's a picture, but you have to be able to do it algebraically. Algebraically means that we can use slope, which is a definite. If any two slopes are the same, then it cannot be a triangle or distance formula. And we have to kind of hope that rounding doesn't mess anything up. But it is a correct approach. All right, we're going to wrap it there.